Well, first I'd like to thank the conference organizers for giving me the opportunity to speak with you today about some of my thesis research in low-mass stars, continuing this trend of basically learning more about the M-dwarf population. And this is what we're doing. And I'd also like to take a moment to acknowledge my collaborators on this project as well. Okay, so first off, as we've heard, M-dwarfs are really forming the dominant constituent of the stellar population. And this is visualized here on the right in a snapshot from a graphic from Adric Riddell and the Recons team of the solar neighborhood. So looking at the 25 parsecs with our sun here at the center, showing that over 75% of the stars in our solar neighborhood are these low-mass M-dwarf stars. And as we've heard already this week, there's great intrinsic interest in understanding the planet properties of these stars, as well as investigating and assessing their habitable zones and intrinsic properties. So one of the things that, despite the great abundance and preponderance of these low-mass stars, there's still a lot that we haven't learned yet about their binary properties, the properties of their protoplanetary disks, and the planet-forming potential of these systems. And so, of course, all of these three key aspects play into what we can understand about the habitable zones in these systems, the disk truncation that might be altered by the presence of a binary companion, the content of the disks themselves, and the dynamical history and evolution and interplay between the star, the disk, and the planet. And so to investigate this, today I'm going to be talking about two main results. So there we go. One, field M-dwarf multiplicity. So we're looking at just this interior 15 parsec region of the closest, brightest M-dwarfs to measure their binary properties. And then we're going to move outward to the torus star-forming region, 140 parsecs distant, which is about 1 to 2 million years old, to understand the protoplanetary disk properties of much younger analog systems. So starting off with the binaries, the first thing that I'm going to talk about is our M-dwarfs in multiples, or M&M survey. So this is a volume-limited survey of 245 stars within 15 parsecs. And we can see that plotted here, these are all about 500 stars within 15 parsecs of the sun from the Hipparcos satellite. We're looking at the brightness and V magnitude versus the color, and we're focusing on this region here of the early M-dwarf stars. And the early to mid M-dwarfs also have a nice match with the target selection that will be upcoming for example, the TESS mission, which will look at the nearest brightest M-stars. With this population, we're searching for stellar and substellar companions. So looking for binaries with orbital separations from about 1 AU all the way out to 10,000 AU. And we're doing this with a combination of multi-epoch imaging approaches. So we have high-resolution new and archival adaptive optics imaging. And this lets us look very close in from about 1 to 100 AU for close binary companions. And we complement this with archival wide-field plate imaging from historic digitized surveys that really give us about more than 50 years of baseline to find co-moving wide objects out to 10,000 AU. So shown here, we can see some of the example companion systems with a variety of architectures, mass ratios between the primary and companion star. And of the 245 stars, we find that about 65 of them have co-moving stellar companions, ranging from as close as about 0.2 AU all the way out to about 2,500 AU. And on the right, we're looking at our survey sensitivity. So this is the mass in solar masses of a companion that we could detect in our imaging survey. You can see that we get all the way down to the bottom of the main sequence, so the transition between hydrogen-burning stars to brown dwarfs and planets. And then we are sensitive to about 3 AU with about 100%, almost 100% completeness to finding companions in this range. So we can take these binary detections, and we can start to look at kind of the aggregate population properties of our nearest M-dwarf neighbors. And so what we're looking at here is a separation distribution. So this is just a histogram of the fraction of systems as a function of the separation of the systems in AU. And what I want to take the takeaway point here to be is that the closer orbital separations are found with these lower mass primary stars. So if we start with A-type stars at about 300 AU, is where we find the typical binary separation. If we move inward to solar-type FGK stars, then it's about 30 AU. And you can see in our red histogram here, we actually don't see the population turnover, but we see the bulk of the binaries are at this sort of 6 to 10 AU separation range, so very, very close, tight binary systems. We can then take our population and look at just the fraction of systems that have binaries at all. And so what we're looking at here is the companion star fraction as a function of primary mass. So the most massive stars here, solar-type stars, our new M-dwarf points, and then the brown dwarf population. And what we see is that we have decreasing multiplicity with decreasing primary mass. Only about 23% of M-dwarfs have binary companions. But what we're really looking at here is that we have fewer binary systems, but the ones that we do have are much, much closer. And this is, of course, going to have really important dynamical interactions with the extent of the habitable zone, dynamical interaction between the disk and the planets. OK, so we're going to move outward now, 140 parsecs distant to the torus star-forming region, shown in the background here. And what we wanted to do here was really understand the dust inventory within disks at these analog systems that are much younger around low-mass stars. And what we wanted to be able to do with these measurements of the disk mass within the protoplanetary disks is kind of get a handle on the planet-forming potential of M-dwarfs and how that might compare to that of higher-mass stars. Then we can take those properties and we can try to understand how they might vary with the mass of the central star, the region, age, and environment. And so this is part of an ongoing survey, the Torus Boundary of Substellar, or TBOS survey, that was started in 2014. We took far infrared detections of the lowest mass stars, the latest M-dwarfs and brown dwarfs in this young star-forming region, with known far infrared detections. We know that they have protoplanetary disks, and we followed them up with ALMA 885 micron continuum observations. And these really give us a handle on the sub-millimeter emission from the dust grains in the protoplanetary disk systems. And shown here is the population that we're looking at that kind of spans the breadth of the torus star-forming region. Oops. OK, so what we found from this survey of 24 targets, which include 10 brown dwarf systems and 12 very low-mass star systems, is that we have 22 detections, which was really quite a surprise. These objects are so faint and young, and the disks, their properties were pretty uncertain before we were able to use the sensitivity of ALMA to measure the disk dust masses in these systems. And so what we're looking at here is an example detection. This is just the spectral energy distribution, so the flux at different wavelengths in microns. And so we see the contribution from the star here, the telltale signature of a disk around the system, and the new ALMA measurement here. And something else you can see is that this is our beam size, the resolving capacity of the ALMA observations to understand the extent of the emission in the disk. And you can see that we're actually starting to resolve these systems and get a handle on what the disk sizes are actually. And so what we can do with these sub-millimeter continuum fluxes, as we heard a little bit before, is we can use these to estimate the mass of dust in sub-millimeter grains for these lowest mass systems. And we find that they range from about 0.3 to 22 Earth masses in total of sub-millimeter grains. So we can visualize this, and I'll step through kind of everything that's going on in this plot one step at a time. Right here, we're looking at the disk dust mass in Earth masses, so 1, 10, 100, as a function of the disk host stellar mass in solar masses. So we have the solar type FGK stars here. We've got the M-dwarfs that really span a broad range of stellar masses, and the brown dwarf regime demarcated here. The red points are our new observations from ALMA, and the background points are what was previously known for the rest of Torus for the higher mass population. You can see that we're extending this well into the brown dwarf regime with these detections. Also plotted here for reference comparison in Heiss-Mulder's talk you just heard are the heavy element masses that are measured from the Kepler FGKM stars. And what we've shown up here to kind of guide the eye is an estimate of what the minimum mass solar nebula should be. So we're saying that from what we know about the solar system, what's required to form Jupiter and the planets in our solar system, if you estimate that to be about 30 Earth masses worth of dust, then you can demarcate this regime as whether or not your disks actually have enough solid material to kind of make it into this region. And what we see is that the early M-dwarfs, and of course the FGK stars, are making into this region. But due to this decline in dust mass as you go to the lowest mass host stars, the lower mass M-dwarfs and brown dwarfs really aren't making it up into this regime. And this is providing some signature, potentially explaining why direct imaging surveys have really focused on the lowest mass M-dwarfs to find directly imaged Jupiter analogs. But it's been very, very difficult to find any of these directly imaged giant planets around the lowest mass stars. And for reference, because we're all very keen on understanding where TRAPPIST-1 and similar systems, these exciting new transiting M-dwarf exoplanet systems lie, TRAPPIST-1 is right here at the M-dwarf brown dwarf regime. And if you take the estimated masses in the planets from the most recent papers, you can see it kind of sits here sort of at the top of that envelope. So this is giving us some idea of maybe starting to look into things like planet formation efficiency of the dust masses into planetary bodies. And one more thing that we can do with these data is we can look at a comparison between the very young 1 million year old torus star family region and that of Upper Scorpius, which is in the 5 to 10 million year range. And so what we're looking at here again is the same axes, dust mass and Earth masses versus the mass of the star. The red points are all of the young torus population, and then this older population is shown here in teal points for this older Upper Sco population. And what we can see is there's about a factor of 3 decrease in the dust mass content from 1 million years to about 10 million years. And so this is giving us some idea about potential timescales for planet formation as these submillimeter grains are converted into potentially larger bodies. And also, I suggest that you look forward to Ilaria's talk, where she's going to be doing more of these comparisons with other types of star-forming regions. OK, so in summary, from these 2 investigations into low-mass stars, we have the binary occurrence is lower for M dwarfs, but they're closer. And this is going to have important impact on our understanding of the properties of these systems. If we go to the younger population and do some investigations in the submillimeter, we see that there's not only this dust depletion, but we see significantly decreased dust masses for the lowest mass stars and brown dwarfs. And maybe this is helping us understand what's happening in terms of the giant planet population, as well as what's going on for the younger analog environments for systems like TRAPPIST. Thank you for your time.
All right, we have time for a few questions. 3 minutes, in fact.
Please come to the microphone and identify yourself, please.
Nice talk, Ilario Pascucci. I wanted to know, when you say that you resolve the brown dwarf disks with ALMA, what was the beam that you had? Oh.
Our beam was about 0.3 to 0.4 arc seconds.
Okay. Yeah. And you always resolve the disks, or you see also unresolved disks?
Some are resolved and some are unresolved, and quite a few are in this kind of marginal regime where they're only just resolved in the UV plane.
OK. All right. So you can give a percentage there or not? What's the fraction?
Oh, the fraction of systems? Let's see. It was actually a bit surprising that both the brown dwarfs and M dwarfs had kind of equal fractions of resolved disks, which then again may say something about the formation processes that are undergoing in the different stellar masses of systems, but kind of close to the 50-ish% range.
Tad Kamasic, University of Arizona. So when you showed that the M-dwarf companion fraction was increasing towards closer separations, that's from direct imaging, of course. So what about RV? What does that say?
Yeah, that's great. So there's a section, that mysterious gap within 3AU where we're not actually sensitive to companions is a perfect place to do the radial velocity and spectroscopic binary population. And there hasn't been a comprehensive survey to look at like a volume limited sample in the same way, but some preliminary estimates and some actually estimates from the Kepler eclipsing binary sample place that even higher. So maybe kind of closer to like the 16% range at max. But it's desperate for like a combination of all the techniques to really get the full population.
Excellent, thank you.
Thanks.
Wait, I had one more question.
Oh, Steve has a
Yeah,
question.
I just wanted to know, those dust masses in the M-dwarfs, are there any correlations with ages of the system that you can extract?
Yes, so we looked at that, and the ages are difficult. So torus is thought to have some spread in age, not just to be 1 to 2 million years, but also to have some intrinsic spread. But from the values that were reported for the ages of the systems that we looked at, there was no correlation between seeing the slightly older torus have a lower dust population. But the age uncertainties are pretty big.
Yeah, OK, thank you.
Yeah.
All right, let's thank our speaker.